Hi, this is Chris, and the purpose of this video is to demonstrate steel beam design functionality in ENERCALC 3D. We'll use this prepared simple model, and I'll just mention that I already have defined some dead load on the model. I've applied some snow load, and then I've also applied some lateral load, wind loads, here at the corners. And then in addition to that, I've also defined some load combinations. Notice that I have my load cases, and then I have several steel design load combinations. And the important thing to note here is that they're all set to yes in the column for steel design. So those will all be considered as steel design load combinations. The next thing that we need to do is make sure that we have current results. So I'll go ahead and run the analysis. The model is completely solved at this point. It's stable. We have a well-built model. And now we can go ahead and start to look at how we set up steel design for beams and how we take off beam design information. What I'd like to do is focus on the design of this one beam. It'll be a fully loaded infill beam. So we'll zero in on that one as we get to assigning information in the steel design menu. The first item that we see in steel is steel materials. This is a view of the materials that we've assigned for analysis purposes, but notice that in this view what it reports to us is not stiffness properties, but instead material properties like the yield strength and the ultimate strength. So in this case, what we might want to do is modify both of these so that they represent grade 50 steel, and then just click apply. Back up to steel. The next item is design criteria. We'll start with model design criteria. The first option is to select the design code. So I'll leave it set to the 14th edition, which references AISC 36010. Notice it'll be an LRFD based design. Then there are some options that we can choose for how we perform the designs. The first option is called Use Direct Design Method. This does not create notional loads. Instead, what it does is it affects the calculation of the moment magnification factor, beta 1. And I'll leave it to the training manual and the user's manual to provide some additional information on the specifics of that option. You can read up on that and decide whether that's appropriate for your design. The second option is whether or not to consider the moment magnification factor beta 1 at all, and we'll leave that set to yes. There's an option to force the program to use a value of 1.0 for CM. If you leave it unchecked, then the value is computed automatically by the program. This option is check capacity at column ends only. We're not focused on columns at this point, so we won't worry about that. This option is to only use sections from what's called the section pool. This note tells us where we'll define the section pool, and we'll see that in a couple of minutes, but in this case I'll just leave it deselected so it'll select from the full AISC database. Connector distance for double angles is only relevant if we're using double angle members, and in this case we're not. The maximum number of steel section candidates is a value that you can set to determine how many possible solution members the program will offer us. And then we have two different values that we can specify as the denominator in our controlling deflection ratios, total load deflection and live load deflection, if we're using those in our design. So I'll click OK, and then come back to steel design criteria, and now we'll go to member design criteria. In this case, what we're doing is we're specifying a series of different options that will control and steer or guide the design of an individual member or any of the members to which these criteria are applied. You can see that I have a couple. The program already comes with one that's called default. I've set up one in preparation called My Beam, and just to show how you can set one of these up, let's call this W16 by something. So this is just a label that we'll use to refer to this set of criteria. And notice, if you look down below, that where we're headed is to apply these criteria to selected members in the model. So now we just head down this path of making a bunch of different decisions that will guide the parameters that ultimately steer the design of the member. The first one being the section prefix. So if we want, we can tell the program that we want it to select from a certain family of members. In this case, I'd like to try to select a W16 for this infill beam. So I'm going to just type in W16, and that clues it in to look just in the W16 family and to go no further than that with its potential solutions. The next two columns relate to whether the member contributes to the stiffness of the structure by flexure about its X and its Y axis. In this case, we're talking about an infill beam, and so I'll say no to both of those. It does not contribute to the stiffness of the structure by flexing about its X or Y axis. The unbraced length, and notice that there's a note up here that says enter 0 for LB if the member is not continuously braced laterally, and if you want to use the member length for LB. So if I didn't have a slab, or if I didn't trust that it was bracing the member, then I could just enter 0 for this, and it would always assume the full member length. In this case, what I'll do instead is enter a value of, say, 1. Now the other option here is to say that the member is continuously braced, and I believe the program is set up so that if I choose yes to say that it's continuously braced, it may come back and tell me that I have to modify that value or that it's going to ignore that value. So we'll set that up and just test that theory to see how the program responds to that. The value of CB has to be entered manually, so you can enter that, take a guess, or be conservative. Then you come to the unbraced lengths, and these are going to be considered in combination with K factors for buckling. For an infill beam, it's really largely irrelevant, but if you were looking at a member that was axially loaded and unbraced so that it had a tendency to buckle about its local X or Y axis or about its Z axis, then you could specify those values and they would be considered for buckling. I'll just satisfy the program by entering non-zero values here for K and L for all directions in this beam, just so that we don't get any messages downstream. And then the last thing that we have is the option to enter a maximum capacity ratio. What's important to understand with the steel beam design function in ENERCALC 3D is that it's somewhat of an iterative process, because we've run an analysis with a certain set of assumed properties. If we design based on those forces, and if we select a size that's at all different, we've somewhat changed the stiffness of the structure, and therefore technically we need to loop back through and reanalyze and redesign, or at least check, to make sure that our selected member still works. Sometimes this can flip-flop back and forth a few times, and it may be that if you have one of those models that's sensitive to that kind of effect, it may help to reduce the number of iterations by padding the design just a little bit and saying, let's not select anything that's so close to 1 already that it's going to be sensitive to the slightest bit of redistribution of forces. And so what I might do is just throw in some number fairly close to 1 but a little lower, and give ourselves a little bit of wiggle room there. Now I've answered all the questions for steel member design criteria, and notice that our target beam is selected in the background, so I can check this box that says assign active criteria to selected members and then click apply. And here is that message that we hinted at where it says I've specified an invalid unbraced length for steel design 3. LB must be greater than or equal to 0. For continuously braced beams, this is us, must be set to 0. Okay, so I'll acknowledge that, come back to LB, set it to 0 to satisfy it, click somewhere else to register that value, and then we'll click apply. So I'll still get the same effect. I still have a continuously braced member, so it won't be subject to lateral torsional buckling. Now we'll come back to steel. We were working in member design criteria. The next item in the list is section pool. So if we happen to have certain members that we knew that we could, that were available to us or that we preferred in the design, if there was reasons for economies of scale, we wanted to try to force the design to certain sections, we could actually list those sections here, and you can do that by clicking the button that says AISC table. And then if we wanted to, we could just scroll down, and I could actually try to force the design to go to a W16 by 36, for instance. I could just select that. That populates one line in the section pool, and then we could say OK, and we would have a section pool started. We can populate it with a number of different sections if we want. The trigger as to whether or not to use it is right here. Only use sections from the section pool during design, or don't worry about it and use any sections that work. So I'm going to just let it do its own thing. I won't force it to use sections that are listed in the section pool, but just know that that option is there, and I can click OK. I still have that one member in the section pool. If I come back to section pool, it's still listed there. So I can populate that pool and then alternately toggle this on and off as I see fit. I can modify the pool as necessary as my design progresses. That's steel section pool. The last thing in the design criteria menu is the option to exclude certain elements from the design. So in anticipation of that, what I might like to do is select the beam that we do want to include and then use this tool to invert the selection so that everything else is selected. Then come back to steel, design criteria, exclude elements, and make sure that the option is selected to exclude the selected elements from steel design and click OK. This way it only focuses on the one beam that we're interested in when it does its design work. Alright, that was a thorough look at everything that's available in steel design criteria. Next, we'll take a look at assign member design properties. This tool is not something that we actually have to use right now because in our case we're only focused on one member and we've already assigned the design criteria. If we wanted to use a section pool, we would have assigned that already. The design exclusion is set up so that this is included, these are excluded, and so on. But if we had gone through and set up multiple design criteria on certain members and then wanted to populate those to additional members out in the model, this is the tool that we would use to do that. So we can choose to assign a certain design criteria to selected members. We can toggle the design included or excluded status, and then we would say assign to selected members and click assign and reset those values, set or reset those values as necessary. So that was under the assign member design properties item. The next item down is called steel member input, which opens the steel member input table. This table lists all the members in the model. It shows what design criteria has been assigned to each of the members and whether each of the members is included or excluded as far as steel design is concerned. So most have the default design criteria and are excluded except for our member of interest, which has been assigned design criteria number 3. and an included status. Notice that we can change the included and excluded status with these drop-down list boxes. And also notice that if we wanted to make a change to the steel design criteria, we can just click on the one we want to change, select the one that we want for design criteria, and then say apply to selected, and now the 3 has become a 2. And to change it back, I can set it to design criteria 3 and apply, and now we can see that the 3 is back. So I'll say OK to that. That was the steel member input table. The next step is to actually perform the steel design. It's very fast in this model because it's a simple model and because we're only asking it to design one member. So we can just click OK. And then we can come to design result. So here we have one table that provides us with the design results for any and all members that we've chosen to design in this model. We can see our one member, its length, the section that was tried, which is the 16 by 36. Notice that it has a no good status because its ratio is just a bit over 1. And then a lot of information about the design, the controlling load combination, where the controlling condition was found to occur, the ratio for axial and bending, shear ratios for both directions. If we had specified deflection checking, we'd see ratios here. Axial force, moment about both axes, shear in both directions. Deflections, phi values, phi PN, phi MN, moment and axial capacities, shear capacities, and then the last items are deflection limit for total load, deflection limit for live load, and the values of CB and CM that have been used. So what we can do in this case is we can pull down the drop down for sections, and what we'll see in the list below is a list of the other sections that the program found that are acceptable. So we might want to try the next item, which is the 16 by 40. Now, when I use that section, notice that the program is set up to yellow out that whole line. This is a reminder to tell us that we've made a change to the stiffness of the model that could theoretically affect the distribution of design forces that were used to obtain this section in the first place. And so the proper thing to do would be to come back in and redesign and then do another check. So if we wanted to do that, what we could do is use the Update Sections button. It tells us that it'll update the sections, but that will invalidate the current analysis and design results, and we can say yes, we agree. Then simply reanalyze, close, steel design, perform design, close, steel design result. And again, if I widen this out, in this case it was an infill beam, and I have not specifically assigned the self-weight function, which is the likely thing that would change that ratio. So when we come back in, we can see that we do in fact have a controlling ratio that's still less than 1, and so that would be a good member for us to use for the design. It's efficient and it satisfies the code criteria. So that's a look at steel design results and the functions that can be used to optimize and then update the model with those new sections. The other thing that I'd point out is that there's a Show Calculation Procedure button down here that will actually open up a new page that lists all of the calculation processes here with formulas and code references and calculated values. So that can be helpful in terms of documenting your design and seeing how the computer arrived at the design that it did. I'll close out of the steel design result dialog and then just back to steel to mention a couple last items. One is that there's a K calculator where you can enter psi values for the column top and the column bottom, and then calculate K factors for the braced or unbraced condition. Just a little design utility tool that can be handy. And finally, under Steel Tools, we have Section Check and Section Design. Section Check is a little utility that allows you to select a specific member and then provide its geometric information like span length, unbraced length, K factors, CB factor, and so on, along with the yield stress, and enter P's, M's, and V's along with CM factors and obtain capacities and ratios. So that's a way to check a specific member for a particular loading. And similar to that is the section design function that allows us to specify a category or a family of members, including geometric constraints on its dimensions, and then provide P's, M's, V's, and CM values along with unbraced lengths and K factors, and then obtain a list of section candidates that would work for the specified loads. And then to go even further, we can select any of those options and use the detail check, which would drill back into the section check dialog and show us all the specific output for a detailed look at that particular member. So hopefully that's been a helpful look at how steel beam design functionality works in ENERCALC 3D.